Okay, so I will use the usual notation for positive integers. Actually, do you know what that is? Do you know what the abbreviation for positive integers is?
No.
It's strangely z plus, written like that, and the rational numbers are abbreviated as q. I have to restrict them to 0 to 1, but let's just pretend for a minute that I'm going to use q to just mean 0 to 1.
Okay.
You can guess where q comes from, probably.
Probably quotient, because they're all fractions.
Z is a little harder to guess because it's the German, Zalen. But anyway, so what we end up actually proving is that with this argument, I'm out of space a little bit. I guess we'll have to let this represent the grid, and I'll erase here.
Okay.
Certainly, the positive integers are inside of this.
Yep, they are.
Okay, even the 0 to 1. What are what's the easiest way for us to say, hey, the positive integers are at least inside of this? Because we were restricted to 0 to 1, so that makes it a little complicated. But there's an easy correspondence with the positive integers.
Well, I mean, integers are sort of defined as rational numbers. You can.
Yeah, but here I'm restricting to just 0 to 1, so there's actually no integers inside of here. But there's an easy way for me to just, using the map that we made, to identify where the positive integers are going.
You could take the reciprocal, I guess.
Yeah, so we could just take a half, a third, a fourth. Now we're missing 1, but that's fine.
Yeah.
Okay, so a half, a third, a fourth, a fifth, that's inside of here.
Okay.
And then the second thing we've done is shown that the rational numbers from 0 to 1 are inside of the thing we mapped to. So I don't know, I'll just call this star, whatever our map was. I went this way, actually. Okay. This had duplicates. So our positive integers are inside of here. We see that from the half, a third, a fourth, a fifth.
Yep.
And now we're going to show, strangely enough, that the rational numbers are also inside of this.
Yeah.
This we transform with our map like this. And why are the rational numbers without duplicates inside of this?
Well, if these things are both subsets of each other, the only way that can work out is if the subset is the maximum possible size subset with all of the elements.
Yeah. If they're both subsets of each other, they have to be the same size.
Yep.
That's the weird thing about infinities. But why are this map that I made here, this diagonal, we said has infinitely many copies of everything.
Yep.
So why are the rational numbers from 0 to 1 in lowest terms inside of this map? Why do I hit all of them?
Well, you're hitting every fraction with every denominator. So you have a rational number is defined as basically a over b, where a and b are in lowest terms, and you're hitting all a for all b.
Yeah.
So
I basically what we showed yesterday is the positive integers are inside the rationals, and the rationals are inside of the positive integers mapped in this funny way.
yeah.
And that's the reason that they're the same size. It's weird to show that a set is inside of something and then that same something is inside of that. But in fact, the only way that can happen is if they're the same size.
Yep.
Which is cool,
Yeah.
right? Mm-hmm. Which is cool. All right, so now, so that kind of completes the proof. This little hiccup. I didn't want to just sort of jump to the next idea without explaining that to you, because it's cool, first of all, but also we've got to make sure we did it right.
Okay.
All right, so now let's talk about the real numbers.